Today we will start with our module 3, that is Turing Machines, RE languages, that is recursively enumerable languages, and undecidability. Right, module 3 consists of these three very important parts, and today in our first lecture of module 3 we will begin with the introduction to Turing machines. So to introduce Turing machine, we will just begin with the question that is it possible to design a formal model of a computational device that would capture capabilities of any algorithm? Is it possible? So you will be astonished to know that ultimately we will come to the conclusion that whenever we will come up with the end of this module 3 section, we will formally prove many things, and we will come to the conclusion that Turing machine is capable of doing everything whatever a computer can do. Can you imagine that about 60 years ago or more than that, a scientist named Alan Turing already proved this concept that using a Turing machine we can implement everything what a computer does, and so that it is capable of implementing or computing anything, any algorithm which exists in real world, right? So Turing machine is capable of doing anything, or if we say in the concept of acceptance of languages and all, we have seen some restriction in case of regular grammars, that this my regular grammar is capable of accepting this much and this much is not possible, or this much is out of control of regular language, regular grammar, or our regular machines like DFA is not capable of accepting this language or processing this kind of languages. Then we move to our next goal, right? That is called push down automata, and it used to accept those grammars called context free grammars, right? And it was a few more criteria was added to the finite machines, and it is capable of doing something else or something better than regular languages or regular machines, right? But when we jump one more step and come to Turing machine, and we will be able to see, okay, whatever the language you are giving, it is able to process everything. Yeah, there are something which is undecidable, which Turing machine cannot compute. That is a second question, but if we focus on our first question, that it will be capable of processing any language given to it, right? We will see it in the later sections. Fine. So Turing machine tried to decompose the operations of a computer into a number of simple steps, and how it decompose, that how the steps will be, that any such step would consist of erasing a symbol on the paper observed by the pencil and writing a new one on its place. What is the meaning of it? That means if you see whatever the finite automata was doing, whatever the PDA was doing, but here the approach is something different. So whatever it is doing is whenever it is encountering any symbol, so whenever it is encountering any string or any set of symbols, the head of that machine will observe it, and it may process it, it may again erase it, and it may also replace that symbol with any other symbol. So you can see it can perform both read and write operation, right? Both the things are possible for Turing machines. Okay, the decision as to which symbol should be written and which symbol should be observed next would depend on the only on the symbol observed by the pencil and the state of mind of the computer. So if we say in this generalized definition or this generalized statement in some formal way, that means whatever the next move this Turing machine is going to do, it will depend on in which state it is now and which input symbol it is processing, right? It is as simple as that. So based on the input symbol and based on the state, it will make one transition. It may be like this, okay, it will stay on the same state, but it will change the input symbol. means not the processed string, it will change it. Okay, it may be the thing is like this. Okay, it will be in the same state and it may erase the processed symbol, it may jump to the next state, whatever the decision, whatever the algorithm will be, it will act accordingly, right? So these are the ways in which a Turing machine process. Fine. Based on these assumptions, Turing suggested a computational device now known as Turing Machine, and that was supposed to implement any algorithm carried out by a computer. So, in our lecture session throughout this module 3, we will try to, come up with some approaches which a computer does, and we will implement that using Turing Machine, and we'll come to the conclusion now. See that computer can do this, so we can implement the same thing using Turing Machine. But it is just impossible to pick up each and every work or each and every algorithm which a computer can process and to show it as an equivalent in Turing machine, right? That will be left with you. You may explore more and more and can find out, okay, this thing can also be done with the help of Turing machine, right? So we will just in our ongoing lecture series, we are going to pick up any one of the problem and we will try to prove it that fine, this thing can also be implemented using the Turing machine, and it will be a successful approach because Turing has already proved it that this can be done. Right. So at first glance, a Turing machine seems to be slightly generalization of a finite automaton. It has a finite control in the form of states, a tape, and a head that can read the tape. As we proceed in this lecture, you will see a diagrammatic approach has been seen, where you will see that there are several states and a tape is there from where it will read its input, and a head, it is controlling, it can move in any direction. We will see it. The only difference is that a Turing machine can also write on the tape and backup to read symbols it read or wrote earlier, right? It keeps a backup with it. It's very essential, and whatever the symbol or whatever, wherever the place it is reading on the tape, it may write it again, means it may put some input of its own according to the requirement of our algorithm. Fine. A Turing machine can simulate processing any data structure using three major components, right? What are the three major components? One is sequence, another is branching, another is looping. So we know that if we can implement these three parts, so we can move to any kind of data structure, we can implement any kind of data structure if Turing machine has the capability of sequencing, if it is having the capability of branching or looping. So all the testing conditions can be carried out, every data all the testing, that whether this condition satisfies, we will move to this state, or if not satisfies, we will do this and that. So all this form of approaches can easily be implementable, right? Now, finite automata are not capable of such testing at all, while push-down automata can do this in very limited form of testing the emptiness of a single stack. We have proved it, that how a PDA is testing whether the stack is empty and not, right? So we have implemented few things. Again, finite automata are not capable of testing anything. It is not, it has no property, right? But push-down automata is having a limited property. So if you go on with the approaches that number of A's and number of B's are equal or not, so push down automata is capable of doing that. It may test the test by emptying the stack or by moving to the final state, whatever the approach we will think of, but still it can do something, but it's very limited. But Turing machine can do everything, right? Now we will see one thesis named it came 60 years earlier from now, called Church Turing thesis, and it says that every computer algorithm can be implemented as Turing machine. This itself has very important consequences for computer science, right? So Church Turing thesis was mainly based on this fact that every computer algorithm can be implemented as a Turing machine. So it's a very, so you can say that it is such a thesis, or it was such a important evidence for us, it was such an important approach for all of us in this computer science domain, that I think Turing should Turing should earn a Nobel Prize at least, right? So it was such a huge evolution, new approach come to our domain. Fine. So Now, whatever the details of this charge Turing thesis is, you will find it in a document that will be I will be sharing you along with this study materials and this lecture series. So just go through it once. What was the basis of the thesis? What were the assumptions and all? Just to make a note of it, nothing else. So just read it out and. This was the beauty of this charge Turing test, is that it proved that every computer algorithm can be implemented as a Turing machine. Okay, so let us directly move to the definition of Turing machine now. The machine consists of, you can see that a tape is there, right, and some x1 x2 symbols are written, some b symbols are written, and a finite control is there. So what are the meaning of these things? So you can see this machine consists of a finite control, which can be in any form of finite, in any of the finite set of states, right? It can be at any state, whatever the state it is processing now, it will be in that state only. Right? There is a tape divided into squares or cell. Each cell can hold any one of a finite number of symbols, right? So now you can see it is processing the xi block. So it may consist of any finite number of symbols. Fine. Initially, the input, which is a finite length of string of symbols chosen from the input alphabet, is placed on the tape. So whatever the input alphabet will be, which we denote using capital sigma, that will be put it inside the it will be placed inside the tape, and the finite control is going to process it one by one. It may erase it, it may change it, whatever the requirement is. Fine. So all other tape cells extending infinitely to the left and right initially hold a special symbol called a blank. So we will use blank symbol B. That means we have not put any any input symbols or any strings in it now. So the whatever the string it is processing, it will be in the tape, and the spaces right to the end of that string and the spaces left to the end of that string or the beginning of that string will be kept blank, and we will use the letter B to denote those places. Okay, the blank is a tape symbol but not an input symbol. Obviously, blank means we are just using that symbol blank to depict that these cells are not yet occupied by any input string. So that will not be a part of input symbol, obviously, and it is a special symbol to denote these places are blank, and it is kept with the tape symbols only. It has no relationship with the input symbol. Fine. Now it has a tape head that is always positioned at one of the tape cells, and the Turing machine is said to be scanning that cell. Right now, if we concentrate on our diagram, we will see that it is now scanning the xi block of the or xi cell of the tape, right? Initially the tape head is at the leftmost cell that holds the input. Obviously, whatever the input string we are going to process in whatever the form of automata is, it may be finite, it may be push down, it may be Turing machine, right? So we keep always process the string from left to right. So whenever it will start processing, it will be at the left, and gradually it will keep on moving to the right until and unless it it is done with the string, right? Whatever the string is given, if it has reached the end of that, then the work is done. Firstly, it will start with the leftmost position. A move of the Turing machine is a function of the state of the finite control and the tape symbol scanned. So whatever it is scanning, so the movement will be accordingly. So now see what are the moves in the Turing machine. In one move, what are the thing it can do? It will change the state. The next state optionally may be the same as the current state. So we know that for any machine or any automata, the movement may be like this, that we are moving from one state to another, and in some cases it may be the same state only. We can move from one state to itself only. It is nothing new. Okay, write a tape symbol in the cell scanned. I already told you that whatever the tape symbol it is scanning is a special criteria of Turing machine. It can write there as well, right? So this tape symbol replaces whatever symbol was there in that cell, and optionally the symbol written may be the same as the symbol of the currently there. So it may write with the new symbol. Means approach may be many things. There are many algorithms where the replacement is like this, that whatever the previous symbol was there, it wrote that symbol only. So according to requirement, it may write the same symbol, it may write different symbol, or it may not perform any write operation at all. So everything depends on whatever algorithm we are approaching. Fine. So here now see, there is a beauty of this Turing machine, that this step head means that finite control head, or that pointer may move from left or move to left or right. So you can see this is main approach. In case of finite automata, there was no concept of memory, I forget about that. Now when we move to PDA, there the approach was only one way, right? So we failed to test that whether the language e to the power n, b to the power n, c to the power n was context free or not. We concluded that it's not context free because PD is not going to process it. It can compare maximum 2, right? Because only one stack was there. It pushed at the first end, then after completion of total A part, then it when it come to the enter into the computing the number of B's, it kept on popping off each A symbol from the stack, and whenever the stack is empty and no B remains, that means okay, and B where the number of A's and number of B's were equal. But whenever C to the power n comes along with this, there is nothing to get compared to. Now stack is empty, with which you are going to compare C. So PDF failed there, right? But here if we can move both left and right, you can see that this approach is also solvable using Turing machine, right? It can compare anything, it can accept any language, right? So it's a very important part of Turing machine. Okay, so now if we have to depict our Turing machine formally, so how we are going to do? Again, here there will be 7 tuple representation. You can see Q, sigma, tau, delta, q naught, b, f. So everything unknown to us except this b. B means the blank symbols, right? Q means the finite set of states, sigma the finite set of input symbols, and tau the complete set of tape symbols. In case of your PDA, we represent this tau as a stack symbols. Here we are not using stack because stack is one-ended data structure. Here we will use a tape like structure where the movement of the finite control is possible in both the direction. So here the total tape symbols will be this tau. Now sigma is a set of input symbol, but it will always a subset of tau only, right? So whatever the input symbols we are placing on the tape, means whatever the tape consist of now, or whatever the machine is going to process, that the input symbols only. So the tape symbols will always the part of input symbol, but except this B, right? This blank symbols. Blank symbols are left with this tape symbols only. It is not the part of input symbol, but whatever the input symbol consists of, it will always be a part of tape symbol. Okay, now let us discuss of the transition function. This delta transition function is depicted with this form, that is delta of q comma x. That means delta of the state it is processing now, and q means input symbols it is going to process. After that it will generate a new thing, that is PYD. So what is the meaning of P? P is the next state which this transition function is transiting to. Means after getting this input x at q state, to which state it is going to move. This P, that is newly generated state or the next state, may be same as that of the initial state, or it may be different. Y is the symbol in tau, means what is the next symbol it is going to process. Written in the cell being scanned means whatever the replacement is been done, it sometimes it may be same, right? We know that the replacement may be same or something may be new. So what changes it is doing at that place. And D means in direction, right here. So this should be there. So whether it has moved left or right, that is mentioned in the D part, that is direction. And now here small q is the start state, B is the blank symbol, it is in tau but not in sigma, and F is the set of final state or accepting states. Remember, it may be one or it may be more than one. Fine. So this is just a very short overview of Turing machine, that how it works, what is the formal representation of it, what is the meaning of each and every symbol in the tuple representation and all. So next day we are going to learn about the instantaneous description of Turing machine. It's a very important part. We have, before going details into the Turing machine, we should at least learn how to represent a Turing machine, what is the instantaneous description, or what is the idea of Turing machine. So we are going to cover this part in our next lecture. This much for today. Thank you.